Hi, my name is Siham Adus. My lab introduces Newton's second law and how it is used when observing an object in constant velocity. Newton's second law states that the change in velocity is equal to the net force divided by the mass times the change in time. Assuming F net, our total force, is constant during a small time period, delta t, we use Newton's second law to explain an object's constant motion or change in motion, and furthermore to predict its new position. In my lab today, I will focus mainly on how we use Newton's second law to explain an observation we could make of an object in constant motion. In order to do so, we have to assume that the net force on the object is zero, giving us the final velocity is equal to the initial velocity. In my experiment, I observed the motion of a hairspray bottle top roll on a table. In order to avoid including the data from the object's initial acceleration, I used the middle of the clip to begin my analysis on tracker. First, I calibrated the scale of the film by including the length of the ruler in the background of the film. Then I determined my axes, aligning the origin with the center of my object. Because I was rolling the top on a flat, leveled surface, I made sure the angle of my coordinate system was 0. After determining the center of mass, I captured the top's initial position at t is equal to 0. I repeatedly tracked the change in position of the object over small intervals of time. It is important that we analyze the object's change in position over small periods of time in order to ensure our total force is approximately constant and we could use Newton's second law. Now, in order to compare my experimental observations with a computational model, I used VPython to visualize the predicted change in motion. For the model to compare to our experimental analysis, I used the initial position from tracker as my position vector and calculated the initial velocity from this data to use as my initial velocity vector. Assuming our object is moving at a constant velocity, I set the fnet vector equal to 0. This program calculates our object's change in position every 0.01 seconds for 1.4 seconds by iterating through the while loop and determining a new position at every point. Here, I extracted the data from the computational model and compared it to my experimental model using two line graphs. The solid orange line represents our predicted computational data, and our data from tracker is represented in blue dots along that line. Although the computational model does not perfectly fit our observed data, we see that both linear models follow a very similar constant change in position, and thus we can conclude that our observed object was moving at approximately a constant velocity. If the object is moving at a constant velocity, Newton's second law states that the object has to have a net force of 0 newtons acting on it. In this experiment, we could assume that the force I initially exerted on the top in the negative x direction negated the frictional force from the surface of the table in the positive direction, as well as the force of air. Also, the normal force on the object in the positive y direction negates the gravitational force in the negative y direction. When examining possible errors in my experiment, I think that the force exerted on the top was not completely negated at the beginning of our filming, causing our observed motion to move at a faster velocity than our predicted. Also, although the table seemed to be parallel to the ground, there may have been a slight tilt, causing the top to roll downward at a faster velocity than predicted. Nonetheless, in conclusion, our experiment supports Newton's second law by showing that the change in velocity is proportional to the total force placed on the object. If the total force is equal to 0, then our object continues to stay in motion with a constant velocity, where the final velocity is simply equal to the initial velocity.